All right, let's start.
All right. Hello, everyone. My name is Jalal Muhtasib,
My name is Edwin Tong.
and we are Group 2. And with the presentation that we had was a proof by case method. A couple of quick information: we CompSci 3, Section 31523. Our professor is Tracy Kosher, and it is February 2024. So let's start with the method of proof. What is proof by case method? The proof by case method is the idea of making a large and unmanageable proof easier by breaking down the proof into smaller and much more manageable segments and conditions. The conditions should cover all possible cases and claims should hold true for every case. Proof by case must show that a statement is undeniably true for each different configuration, and as such, this proof for longer and more diverse theorems takes a much longer time.
So here's how to set up proof by cases. Proof by cases follow a similar format to other different types of proof where the theorem is the same, but the proof is handled differently. So as you can see, the theorem is the same, but the proof is split into multiple cases where the proof usually have a large domain and the case handle a part of that domain, so it wouldn't be too much of a hassle to handle. So one example of a proof by case is this. So the theorem is that any number that is raised to a positive even integer that is greater than 0 will have the same parity, meaning it will be even or odd. So proof, assuming an even number is x equal 2k and an odd number is x equal 2k plus 1. Now, in this proof, we have the domain of every number, so 0 to infinity. So that is a large domain. So I basically split up into two different cases where in case one, the number is even. As you can see, x is equal to 2k. So if you plug in the expression 2k to the power of 2, it gives us 4k to the power of 2, which simplifies to give us that 2 times k is to the power of 2, which is even. So in case one, the number is even when it's raised to the power of 2. In case two, the number is odd. And as you can see, the math works out to x is equal to odd number. So it will still have the same parity. So as you can see, the domain is basically split in half, and we cover both cases where the the theorem is true. In example 2, we have a different theorem. Any number raised to a positive odd integer will have the same signs as its original number. So what I'm talking about is raising to like the third power or fifth power, and it will have the same, it will be either positive or negative. So assuming that x is negative, which means that x is below 0, and x is positive, which means x is above 0. So this time we're dealing with numbers from negative infinity to positive infinity. So we split it up into two cases like before. So case one, the number is positive. And if you read the proof here, a positive number times another positive number will always give you a positive. So that's pretty self-explanatory. But case two, if you multiply an odd number of a negative number, it will still give you back an odd number. So just like that, we cover negative infinity to positive infinity just by doing proof by cases.
All right, so now let's connect everything that was said above with an actual Python code. So over here, we just want to see if x, which could be any random integer, is is it even or if it's odd. So we have two cases. If x is even, in this function, it first checks if x, which is our integer, is even by evaluating x divided by 2 equals 0. Over here is just checking if any random integer, let's say 4, if it's divisible by 2 and the div is 0, then it is even. Thus, it prints out that for any given x, for x, x is even. Else, it goes into the second case, which is the only other possible case for the scenario in which x is odd. In this case, it just prints for x and then prints out the actual x. It says that x is odd. And with that, we check all possible cases and as such, we prove that x is either even or odd. And once again, guys, we'd like to thank you, and have any questions, please leave it to us.
All right, hold on, guys.